2022 AP Calculus AB free response question number 2. So we're given a graph here with two functions, so let's read the question. Let f and g be the functions defined by f of x equals natural log of x plus 3 and g of x equals x to the fourth plus 2x to the third. The graphs of f and g shown in the figure above intersect at x equals -2 and x equals b, where b is greater than 0. So at this point in the video, if you'd like to pause and take a look at A through D and see if you can figure these out on your own, that would be encouraged. I'm going to progress through each part, one on each slide throughout this video. But before we move on to part A, let's take a look at some key things about this graph. Whenever we have two graphs in the picture, and once you perused through parts A through D, you would come to the conclusion we're going to need to know what graph is, or what function curve is what on this picture. So to start, we have a calculator available to us, but we can also just use our knowledge of functions to quickly determine which one is which. We should know what the natural log of x looks like, and we should see from this function f of x that it's been translated to the left 3 units. And that is going to allow me to conclude that that function I've outlined in red, or highlighted in red, is our f of x function. Then when I move over to g, we have no other choice but to conclude that the other function is g, but we should also feel good about that. Our leading term, x to the fourth, indicates end behavior as we go to positive and negative infinity, where the function should go to positive infinity on both, and we see that there. And also, to make sure that this is definitely the g function, we can see by this function equation that when x is equal to 0, the output is also equal to 0, indicating we have a point of 0, 0, which this graph does pass through, and the other one does not. So we know our second curve that's below is definitely our g function. So I'll outline that now. Now, one last piece of information we should try to find before we start this problem, because we're going to need it, is this point of intersection that they have designated as B. So we're going to be able to find that using our calculator pretty easily. I'm using a TI-84, so what I'm going to do is I'm going to graph both functions, so feel free to determine what the equivalent process would be depending on what calculator you're using. I'm going to graph f of x in one y equals position and g of x in the other. And upon graphing these two, we're going to go to the calculation list in our calculator to determine where do these intersect. We have 2 points of intersection in this region of the graph, and one was already given to us -2, so I'm looking for that other point of intersection B, and when I find that, I put my cursor on one curve, my cursor on the other curve, hit enter, and it'll allow me to guess. I put my cursor near that point of intersection as close as possible, and then we find out that that point B, the x value of that point of intersection, is 0.78197514. Okay, so I think we're ready to move on to part A. So part A asks us to find the area of the region enclosed by the graphs of f and g. So the area of that region, anytime we have area under a curve, we know, or the signed area under that curve and the x-axis is going to be calling for an integral. In the case where we want to find the area between curves, we're going to integrate the top function minus the bottom function in that region. So it is asking us to just specifically look at from -2 to b. So we're going to say the area is equal to -2 to b. And at this point, we're going to acknowledge what b is, where b is equal to that value we wrote down before. So we can say in here, we're going to do f of x minus g of x to show the greater what integral we're computing. We're going to get an area value from this. And in this case, the answer is going to be, when rounded to 3 decimal places, 3.604. So this is a 3-point question. we're going to get 1 point for the integral that we've written down. So what are we actually computing? We're going to get another point for the correct lower and upper bounds on our integral. So having that -2 and also having the correct b value. We've written capital B, which is fine as long as we're acknowledging what the actual value of b is. And then we're also going to get a point for our area. And just a reminder, when rounding 3 decimal places. So how are we getting this actual value in our calculator? Once again, I'm using a TI-84. So what we're going to do is go to that integral calculation ability of the calculator. I'm going to input that b value up top. And then when I type in my integral, we're going to have ln x plus 3, and then we're going to subtract. So here's where we have to be careful, because we need to subtract this entire g function. So we need to make sure we either distribute a negative through that or put parentheses around that function to indicate the entire thing is being subtracted. So just be careful on that input there, because we won't get the correct answer, and we're going to integrate with respect to x. So there's our calculator input to get that final answer, putting parentheses around that second equation, or like I said, if you want to distribute the negative here, you could write it like this instead, and we should get the same result. So there's part A. For part B, along that interval from -2 to b, let h of x be the vertical distance between the graphs of f and g. Is h increasing or decreasing at -0.5? And then give a reason for your answer. So if we want to determine when a function is increasing or decreasing, we're going to evaluate its derivative. So we're going to need to work with h prime. We'll know it's increasing if the derivative is positive at this specific point, -0.5. If it's decreasing, the output of the derivative at that point will be negative, and that will be our reasoning as well. So we need to define h. H is the vertical distance, so let's define it in terms of a function. So the vertical distance between two curves is just going to be the top curve minus the bottom curve. So h of x is f of x minus g of x, which means h prime of x, when we differentiate a difference, that ends up being the difference of the derivatives. And we're trying to determine, well, what's the value of this derivative at -0.5? So for this computation, in my calculator, it will differentiate for me at a specific point. So to evaluate what this is going to be, we're going to make d dx. We're going to type in ln x plus 3. So I'm going to ask it to differentiate. So to determine where that purple arrow came from, this part here is what I'm going to type in the parentheses on the calculator, where the calculator is going to take the derivative of that thing in the parentheses. So just allow the calculator to actually compute the derivative. For many of you, I would hope that computing this derivative is not too difficult. We just have some power rule here, and then just using some chain rule accompanied with just differentiating a natural log. But even the chain rule will have a derivative of 1 for the composition. So not a difficult derivative to compute, but once again, if the calculator can do it for us, there's less room for error on our part, so we should allow that to happen. So we're going to do minus, and again, we're going to put that second function in parentheses, and we're going to evaluate it at x equals -0.5. And then upon that evaluation, we're going to get our output value for that derivative h prime at this point. And that output value is going to be -0.5999, and it goes on for a few, so to round to 3 decimal places, I'm going to write, I guess you could write 0.6, but I'll just write 0.66 or 0.600 for that 3 decimal places. So now that we've gotten the output at -0.5 for our derivative, we can now give our answer. So the original question is, Well, is it increasing or decreasing at that point? We now know that h of x, the vertical distance between the graphs of f and g is decreasing. We're going to specify where, right? Because it could potentially not be decreasing at other points. At x equals negative 0.5 because h prime of negative 0.5 is less than 0. So we gave a reasoning, we gave a final answer. It is decreasing. The reasoning why is because the derivative is negative at that point. So what's the point breakdown? We're going to get a point for considering the derivative. Okay, so what do we actually need to look at? And then we're also going to get 1 point for our answer. So 2-point question there. On to part C. The region enclosed by the graphs of f and g is the base of a solid. The cross sections of this solid, taking perpendicular to the x-axis, are squares. So find the volume of the solid. So to find volume, we're going to consider an accumulation of the areas of the cross section. And anytime we're accumulating something over some interval, that calls for an integral. And we're going to integrate from -2 to b. So to compute this in general, so our volume is going to be, we're going to integrate from one point to another, the area formula for our cross sections, right? That's the idea. So the area of our cross sections are going to be determined by the side length of that cross section squared. Because we're working with a square, we know the area of a square is equal to s squared. So we have to determine, well, what's s? When I look at this picture, when being told that the cross section runs perpendicular to the x-axis, the length of that cross section that I've just drawn, that we have to imagine, this is like a bird's eye view down on this plane. Okay. So that top view with that purple line I just drew is going to represent one of the sides. And that length of that line, as we've just been doing in the previous parts, is the difference between the top function and the bottom function. So we're going to say that s, the side length, is going to be f of x minus g of x. So side squared, which is our area formula, is going to be this difference squared. So now how do we find the volume? Well, we're going to integrate. So our volume is going to be the integral from -2 to b. And again, acknowledging b is that nice long decimal of f of x minus g of x squared dx. So this is the computation we're making. We're going to take care of this in our calculator. Don't forget to type in that squared part when you're typing it into the calculator, because otherwise, if you forget the squared, you will get the exact same answer as we got in part A. And that should be a red flag because the area of that region will not be equivalent to the cross-section region when you have these shapes that are extended up into a third dimension. So that should have been a red flag also, but forgetting that squared, common little mistake here. So make sure you input that. We're going to obviously replace f and g by their respective equations, the natural log and that quartic function. So now when we make this computation, we're going to get 5.340. So the decimal for this volume would have extended beyond 3 decimal places. And once again, we are rounding to that third decimal place. So what's the point breakdown? We're going to get 2 points for this. We're going to get 1 point for our integral, and we're going to get 1 point for our answer. And now let's move on to the last part, part D. A vertical line in the xy plane travels from left to right along the base of the solid described in part C. So we have that vertical line. So the base of the solid was described as that area in that enclosed region. And we know that solid was formed by looking at cross sections that were squares. So that vertical line that I just drew is going to represent one of the sides of the squares that form the cross sections that ultimately form the entire solid. So this vertical line is traveling along this base. which is that area enclosed, and it's going from left to right, so it's going to be moving that way. The vertical line is moving at a constant rate of 7 units per second. Okay, so that's going to be some important information there. Find the rate of change of the area. So rate of change, that's going to call for, we need a derivative, and it's of the area. So we need an area formula, and we're going to have to differentiate that. Okay? So the area of the cross section above the vertical line with respect to time when the vertical line is at a certain position. Okay, a couple of key pieces of information here beyond that initial thing we just talked about, rate of change, units per second. So here we go. We have to, one, differentiate with respect to time. So we recognize from this portion, we're going to need a derivative of the area, but when we differentiate, it has to be with respect to time, and we want to know what's happening at the specific point. So here's the key to this problem. One, area is defined by position. So we determine the area of the cross section depending on where we are positionally in the XY plane. But as stated in the second sentence, the position of this line that represents the base or the side of our cross section is changing with respect to time. So we have to differentiate this area formula that's defined by position with respect to time. So we need to recognize, well, the position is changing with respect to time as well. So let's redefine x not just as a single value or variable, but also as a function itself that changes with time. Okay, so area depends on position, and now the position is going to be dependent on the time. Okay, so when I rewrite my area formula like this, we can recognize there's a composition here. And now that I have a composition, we're going to perform that chain rule when we differentiate. So if we want to take the derivative of this, ultimately with respect to time, we're going to have to find the derivative of the area with respect to x initially, but then by chain rule, we got to differentiate what's inside, so we're going to find dx dt. Okay. Now, what is dA dx? Well, we have our area formula from the last part. F of x minus g of x squared. And when we differentiate that, we can take care of this in our calculator because we're going to ultimately do this at a specific point. So when we want a prime of negative 0.5, there's no need to try to do this derivative by hand. We're going to do d dx in the calculator, and we're going to type in our ln of x plus 3 minus x to the fourth plus 2x cubed, square it. Let's make sure I just have the correct number of parentheses here. Well, not dx, but evaluated at negative 0.5. So that, when evaluated at negative 0.5, is going to get us this part of the computation. And now what about this part? Well, the dx dt is given to us. It's telling you how the position is changing with respect to time. That's what I have circled in black here. It's 7 units per second. That is a rate of change. So dx dt is just 7. So whatever we get from this computation of a prime at negative 0.5, we just multiply it by 7, and that will tell us the rate of change of the area with respect to time at negative 0.5. So let's make that computation. So I made the computations in my calculator. We determined dA dx evaluated at negative 0.5. So this value here is going to be negative 1.324 and a couple more decimal places. We established before there was given information on how the position changes with respect to time. It was 7. And upon multiplying those two things together, we get what? The derivative of the area with respect to time is going to equal negative 9.272. So how are we going to interpret our answer? We're going to say, scroll down here. So at position, x equals negative 0.5. The area, or I'll say the rate of change, is negative 9.272, and I think this is just in units, so square units, and then there's no specific units here, so just general units, and then it was measured in seconds. So square units per second for the area of the cross section. And that's all there is to it. So what's the point breakdown? We're going to get 1 point for recognizing a chain rule is needed. So let's kind of review why that's necessary. So this first part here, it asks you to differentiate the area of the cross section, but the area of the and it says with respect to time, but the area of the cross section is dependent on the position. So area is dependent on position, but now position's dependent on time. So when we differentiate area with respect to time, I first differentiate the area with respect to position and then multiply how the position is changing with time. And that's why the chain rule was necessary there. So if you redefine that input x as a function of time itself, like we did initially here, that can help you recognize that a chain rule is needed by making the composition obvious. So we get a point for that recognition and showing that that's what we need to do, and then we also get a point for our answer. So a 2-point question here where the answer is stating that at that specific position, right? So we want to make sure we are recognizing or showing that the grader, we're recognizing that at this specific position, the rate of change is this for the area of that cross section. So that is all of question 2 for the 2022 AP Calculus AB free response section.